Welcome back to Decentralized Application Development Crashcasts. I'm Sheila, and as always, I'm joined by my brilliant co-host, Victor. Before we dive in, I want to remind our amazing listeners that if you're enjoying our content, please rate us on your favorite podcast platform. It really helps us reach more developers like you.
Absolutely, Sheila. Your support means the world to us. Now let's get into today's topic. We're continuing our journey through Chapter 3 of Season 1, where we're exploring distributed hash tables, or DHTs. Today we're going to take a deep dive into DHT algorithms.
That's right, Victor. And to kick things off, I've got a brain teaser for our listeners. Here's the quiz question. In a network of 1 million nodes, which DHT algorithm typically requires fewer hops to locate a key? Chord or Kademlia?
Ooh, that's a great question, Sheila. It really gets to the heart of efficiency in DHT algorithms. Without giving away the answer, I think our listeners will find it interesting how different approaches to organizing a distributed hash table can lead to significant performance differences. Let's keep that question in mind as we explore these algorithms.
Absolutely. Now, before we jump into the specifics, could you give us a quick refresher on what a DHT algorithm actually does?
Of course, a DHT algorithm is essentially the set of rules and procedures that determine how nodes in a distributed hash table organize themselves, store data, and look up information. It's like the blueprint for how the entire DHT operates.
That makes sense. So let's start with one of the most well-known DHT algorithms, Chord. Can you tell us about its key features?
Certainly, Chord is a landmark DHT algorithm that uses a circular key space. Imagine a giant clock face, where each node and key has a position on the circle. The clever part is how Chord handles lookups. It uses what's called finger tables, which are like shortcuts around the circle. This allows nodes to quickly jump to approximately the right location, making lookups much faster than a linear search.
That's fascinating. So if I understand correctly, it's kind of like having a phone book where you can quickly jump to the right section instead of flipping through every page. Is that a fair analogy?
That's an excellent analogy, Sheila. Just like how you might use the alphabetical tabs in a phone book to quickly get close to the name you're looking for, Chord uses its finger tables to make big jumps around the circle, getting closer to the target with each hop.
Now, you mentioned Kademlia earlier in our quiz question. How does it differ from Chord?
Great question. Kademlia takes a different approach. Instead of a circular structure, it uses what's called an XOR metric to determine the distance between nodes. It also introduces the concept of K-buckets for managing node contacts. These features give Kademlia some unique advantages.
XOR metric, K-buckets, those sound pretty technical. Could you break those down for us?
Of course, the XOR metric is a way of measuring how far apart two nodes are in the network. It's calculated by performing an XOR operation on the node IDs. As for K-buckets, think of them as contact lists that each node maintains, organized by distance. The K in K-bucket refers to the maximum number of contacts stored in each bucket.
I see. So how do these features make Kademlia different from Chord in practice?
The main difference is in how they handle lookups and node organization. Kademlia's XOR metric allows for more flexible routing, and its K-buckets help maintain a well-distributed network of contacts. This often results in faster lookups and better resilience to node failures compared to Chord.
That's really interesting. Are there any real-world implementations of these algorithms we should know about?
Absolutely. Kademlia, in particular, has seen wide adoption. It's used in the BitTorrent network for decentralized tracking of peers. The Ethereum network also uses a modified version of Kademlia for its peer discovery mechanism.
Wow, so these aren't just theoretical concepts. They're powering some major decentralized systems. Are there any other DHT algorithms we should be aware of?
Indeed, there are. Some other notable DHT algorithms include Pastry, which combines elements of both Chord and Kademlia, and CAN, Content Addressable Network, which uses a multi-dimensional coordinate space. Each algorithm has its own unique approach to solving the challenges of distributed key-value storage and lookup.
It sounds like there's a lot of innovation in this space. what are some common pitfalls or misunderstandings developers might encounter when working with DHT algorithms?
Great question, Sheila. One common misunderstanding is assuming that all DHT algorithms perform equally well in all scenarios. In reality, the choice of algorithm can significantly impact performance based on factors like network size, churn rate, and the types of operations being performed. Another pitfall is underestimating the importance of proper network maintenance. DHTs require ongoing effort to keep the network healthy and efficient.
Those are great points, Victor. Do you have any tips or best practices for developers working with DHTs?
Absolutely. First, thoroughly understand the properties of different DHT algorithms and choose the one that best fits your use case. Second, implement robust error handling and retry mechanisms to deal with node failures and network partitions. Finally, consider implementing some form of caching to improve lookup performance, especially for frequently accessed keys.
That's really helpful advice, Victor. Now, before we wrap up, I think it's time to reveal the answer to our quiz question. In a network of 1 million nodes, which DHT algorithm typically requires fewer hops to locate a key? Chord or Kademlia?
Ah yes, the moment of truth. The answer is Kademlia. In a network of 1 million nodes, Kademlia typically requires fewer hops to locate a key compared to Chord. This is due to Kademlia's XOR metric and K-bucket structure, which often result in more efficient routing. However, it's important to note that performance can vary based on specific implementations and network conditions.
Fascinating. To wrap up, let's summarize the key points we've covered today. We discussed two major DHT algorithms, Chord, with its circular key space and finger tables, and Kademlia, with its XOR metric and K-buckets. We learned that these algorithms have different approaches to organizing nodes and looking up data, which can result in different performance characteristics. We also touched on real-world implementations, common pitfalls, and best practices for working with DHTs.
Excellent summary, Sheila. I hope our listeners found this deep dive into DHT algorithms informative and engaging. Remember, understanding these algorithms is crucial for building efficient and scalable, decentralized applications.
Absolutely, Victor. And to our wonderful listeners, we'd love to hear from you. Visit crashcasts.com to join our Discord community, where you can discuss today's topic and connect with other developers. If you're enjoying our content, please consider supporting us on Patreon. Your support helps us continue creating high-quality, educational content for the decentralized development community. Until next time, keep coding and stay decentralized.